Okay, Bohr model. So here we have a picture of a neon sign. This orange light that's produced here is actually from the element neon. It's a gas at room temperature. They put it in these glass tubes and they zap it with electrical energy, and it gives off this bright orange glow. What's happening here is the neon atoms are absorbing the electrical energy and then re-emitting it in the form of light. So they're basically converting electrical energy into light energy. This can happen with other elements as well. This is a mercury lamp. Same idea, but mercury inside instead of neon. It's not nearly as bright, but it gives this nice blue color. And here's a hydrogen lamp. Hydrogen gives off a pink color. Well, why do different elements give off different colors of light? So scientists looked into that. So they took a hydrogen lamp with its pink light, passed it through a slit and through a prism. When we do that with white light, we got a rainbow. When we do this with light from a hydrogen lamp, you get 3 lines. Well, 4. This one's really hard to see down here. You get distinct lines instead of a whole rainbow. And this really gave them pause. Like, why is it doing that? And that leads to investigations and more knowledge. Every time you do it with a hydrogen lamp, you get the same colors. The wavelengths can be measured, and they're always the same wavelengths. So this is almost like a fingerprint for hydrogen, always the same. White light gives you this continuous spectrum. Here's hydrogen. It gives you just selected wavelengths. Notice the colors here match up with the colors on the white light spectrum. It's just that we're missing a lot of the color. So that's hydrogen. This is helium. It's got lines in different places. And then here's neon. So you can kind of tell why neon light is going to be brighter than a helium or a hydrogen lamp, because there's a whole bunch of lines in this visible range. And so it's going to give us a brighter light. So these are called emission spectra. Anytime you do this with an individual element, you get these distinct lines. So why? Why is it distinct lines? So Niels Bohr came up with a simple model to explain this. So in his model, here's the nucleus with the protons and the neutrons. And then the electrons are in orbits around the nucleus. So it's a lot like a planetary solar system, where here's the sun, and then each of the planets has their own orbit, and they're traveling around in these circular orbits. And that is relatively easy for us to understand. So what happens is, say we're looking at hydrogen. Hydrogen has an electron, just the one. And so here's its one electron. When it absorbs energy, that electron can go up to a higher energy level. So as you go away from the nucleus, as the radius of these orbits gets larger, they become higher in energy. It's a little bit like, climbing a ladder. You get higher in potential energy as you climb the ladder. You also have higher potential for breaking yourself when you fall off the ladder. So as you go higher, the energy increases. When this electron returns to a lower energy state, it releases energy, and that corresponds to one of those lines, a particular frequency of light. So the distance from the nucleus and the energy of each Bohr orbit, is fixed. Quantized is the fancy name for that. So on a ladder, right, this is kind of a weird looking ladder, because as we go higher, the rungs get closer together. This is illustrating the energy levels of the orbits in a hydrogen atom. You can stand on the bottom rung, you can stand on the second rung, you cannot stand halfway between, right? It's one or the other. You can't be in between. That's what quantized means. There are set values, and in between is not possible. Our monetary system is quantized, paper currency. There's a $1 bill. There's a $2 bill. You don't see them very often, but it's there. There's a $5 bill. Anybody ever seen a $7 bill? How about a $3 bill? They don't exist. You can't have them, right? So that's quantized. There are specific levels, and you can't be in between. So in terms of these orbits, the electron can be in orbit 1, or in orbit 2, or in orbit 3, but it cannot be in between. What's a little bit hard to understand is how does it get from one to the other if it can't be in between? It can't be in between even for a split second. It doesn't even go in between to travel from one to the other. It just leaps. So here we have energy coming in. There's our electron in the lowest energy state, and it is excited up to a higher energy orbit. That's not stable. It will relax back. It can relax down to the next level. So it went up to n equals 3. It could relax back to n equals 2, or it could relax all the way back to n equals 1. When it does that, it releases the energy that it absorbed in the form of light. The energy of this light corresponds to the difference in energy between the two orbits that the electron is moving from and to. This is a packet of light that's emitted, and the energy of that photon is equal to the difference in energy. The energy of that photon is related to the frequency. We can observe the color and thus measure the energy of that. So a photon of light, a quantum of light, a packet of light. Any questions? So the lines that we see from a hydrogen lamp correspond to specific transitions. So the red line that's observed at 657 nanometers corresponds to an electron going from the third energy level to the second energy level. The blue-green line is from n equals 4 down to n equals 2. And the violet line is from 5 down to 2. The energies of these orbits are quantized. There is a fixed difference in energy between each of them, and as you go out, they become closer and closer together. So there are only particular transitions that are possible, and that's why we only see specific lines of light. So the Bohr model was awesome. It predicted the lines in the hydrogen spectrum. You can do calculations, you can calculate the energies and do all kinds of cool stuff. So they did all that, and it's like, okay, let's look at the next element, let's look at helium. It only works for hydrogen. If you get more than one electron in there, it doesn't work anymore. So we don't completely throw it out because it's helpful to understand the process of how we figured this out. I also like the Bohr model because it's something that you can get a hold of, right? You can imagine a solar system with the nucleus as the sun and an electron as Earth going around. We can imagine that. We can understand that. And so even though the Bohr model is not correct, thinking about it will help us to partially understand the quantum mechanical model.